Hello everyone. The subject of our talk is Tesla hacking 2017, how we remotely compromise the gateway, BCM, and autopilot ECUs of smart cars. My name is Ling Liu, and this is Yuefeng Du, and this is Wenkai Zhang. We are researchers from Tencent Key Security Lab. We are focusing on the research of smart cars. In 2016, we successfully implemented a remote attack on Tesla Model S. In both driving and parking mode, today we will talk about the research we did last year on Tesla Model X, including what we found and how we customized the Easter egg. Our presentation is divided into 5 parts, including how we hacked into the central infotainment display, how we bypass the code signing protection. Besides, we will review the details of OTA process. We will explain how we customize the Easter egg. Finally, we will talk about how we routed APE remotely. At last year's Black Hat, we explained how we utilize 2 vulnerabilities in WebKit to exploit the browser of Tesla. After that, Tesla fixed these 2 vulnerabilities. However, the version of WebKit still kept on 534.34 for a long time. This time, we utilized only 1 vulnerability to achieve arbitrary code execution. This is the proof of concept. It has been public for many years. You may need to test it under ASAN to trigger a crash. So from the code, we can see it is actually a classic UF vulnerability related to transform list element. So to exploit it, we need to figure out when the memory buffer allocated and freed, and what's the memory buffer used for. The result is the memory buffer belongs to the vector, which is variable values, and the buffer is used for storing SVG transform objects. As you can see in the function initialize, a new memory buffer allocated immediately after the old buffer freed, which makes the exploit more difficult. So in our exploit, we use the function clear instead of the function initialize. So we can put the structure we want right in the place the old buffer occupied before. After that, we can access the new structures by accessing the matrix element. From the view of memory, SVG matrix is part of SVG transform. So after buffer freed, we can directly read and write the red air memory by getting or setting the property of matrix. So in our exploit, after the buffer freed, we filled with the structure array storage. We can leak m_alloc base. Because m_alloc base is a member of the array storage structure. Also, m_alloc base is a pointer to this array storage structure. So we leak the heap address by writing the matrix A, by writing the property A of matrix. We can add the m_alloc base to any address. So when array and shift, we can achieve arbitrary address free. Next, think about such a situation. The buffer of uint32 array overlaps with the array storage structure. Then we made a fake string in JavaScript array by constructing a series of fake structures, including string object, JS string, and string info. the length in string info is big enough, so we can read the whole memory through this fake string. After all of this, restore arbitrary address write is not hard, so just write the shellcode into the JIT memory. Now we get a shell on CID. However, the privilege is very low. Last year, we utilized a well-known vulnerability to gain root privilege on CID. However, this time things become different because Tesla upgraded the kernel from 2.6 to 4.4. And of course, PXN is enabled. The message is restricted, so no crash log anymore. Good news is KLSR are not enabled on CID. So our workmate Nielsen decided to find our own escalation vulnerability. Today he can't be here, so I'm going to help him introduce this part of research. According to AppArmor rules of browser, the device-fine nvmap and nvhost control can be accessed by browser. So we mainly focus on the nvmap. nvmap created by Linux driver memory manager for Tegra GPU. User process can send many IO control commands by calling IO control function. When user process call IO control function with command pin, user process need to provide a pointer to the structure nvmap pin handle. And the function nvmap IO control POP will copy these structures from user memory to kernel memory. In this structure, the pointer handles points to an array of nvmap handle structures. The pointer handles points to an array of pointers to nvmap handle. And in the deeper function, nvmap pin IDs will invalidate every nvmap handle structures in this array from start to end in a for loop. So next, if there is an invalid nvmap handle structures, these invalid handle structures and other nvmap handle structures in this array before these invalid structures will be processed by the function nvmap handle put. The function nvmap handle put will decrease the reference of these invalid structures. Since the pointer of these invalid nvmap structures provided by user process, so we can decrease any integer data by 1 in kernel memory. So we decrease the address of accept for in syscall table. Then to an instruction BLXR3. So we can hijack the PC to any address by setting the false argument of accept for. We hijack the PC to GLP gadgets to achieve arbitrary address read and write. What we need is just to set the proper arguments of accept for. To bypass AppArmor, we patched the AG profile mode with AppArmor complaint. We also patched the set RESUID, so we can gain root privilege on CID. Next, Yuefeng Du will be telling you about how to bypass code signing protection.
All right, thank you. Everyone knows that we have bypassed the code signing protection in 2017, but before we tell you how we bypass the code signing protection, let's take the time back to 2016 and see how the code signing protection is added and why it is added. In 2016, we have published a report that we have hacked the Tesla cars, and it involves an important thing in the gateway called the update software, which is the updater. The name of updater is boot image, which is loaded from the SD card, and files on SD card are transferred from the CID via the Ethernet, and also some files on the SD card is written by the gateway itself. For example, some CAN logs and some diagnostic things. And neither signature nor cert is applied to the update software, so we can just upload our modified software directly to the gateway and reboot, then it will run. After we have submitted the bug reports, Tesla added some signature check process to it. The updated software will be checked using the SHA-512 and ED2519. Using those, you can see this function is here. And we also consider to do some cryptography attack. However, we don't think it's really easy because all those constants and keys seem carefully picked. They have really talented engineers. So we turn around to check its implementation. There are two things we need to check. First, how the updater is written to the SD card. And second, how the updater is executed. You can use some protocols to write the file to the SD card. Here is running by the file operate agent. And the protocol is used is something like a TLV style. And so like we have said, there is a length, the command code, and the data. And you can read file. For example, here I want to read file image. And I can also rename a file. For example, I want to rename from file image to used image. However, if you want to transfer the updater, which is named in boot image, directly to the gateway, it's prohibited. Oh, here. Why? Because it's rejected here. There is a code exists here to forbidden a boot image uploaded directly or renamed from an existing file. So how you can transfer a boot image to it? This should be finished by a diagnostic agent. The diagnostic agent also runs its own protocol. We call it a gateway diagnostic protocol. This protocol has a fixed length of 32 bytes, and the related command to transfer update software on it is that reboot for update. It only has one argument, which is the file name. And in the related section, it will verify if the file is correct. You can see it here. Verify some message using the algorithm we have previously talked about, and rename the file if the content of this file is correct and signed by Tesla. So here is the general procedure. You cannot write a boot image directly to the SD card. Instead, the file agent should write a no boot image to the SD card. And second, the diagnostic agent on the CID will tell gateway to check if the no boot image is correct. And gateway, after check the no boot image is signed by Tesla, will rename no boot image to boot image. We have said that the command related here is called reboot for update. So then the gateway itself will reboot. And last year, we have said that the gateway is running our PowerPC chip. So when reset is triggered, there is some code, which we call it bootloader, will be executed first. The bootloader is written by Tesla, and it would check if the boot image exists in the SD card. And if it exists, it will check the boot image have a ret checksum. And if so, it will also check something such as the magic path here. Right? Yeah, here. And try to put it, just copy to the memory area and just jump to there. And maybe you have seen that there is actually a problem here. Bootloader will not check the signature of the boot image in either the first version or the second version. This is because if you want to update the bootloader for the current cards, it is really dangerous. Since if you write a byte wrong, and we will get a bricked gateway. And the bricked gateway means a bricked CID, and it means a bricked car. So you have to send their cars to some workshops. And the most important reason is that without chip-level secure boot applied in the factory, update the bootloader itself is completely useless, because if your gateway code itself have vulnerabilities, it can still be attacked, and you can still operate those SFRs to unlock the flash areas and write another bootloader into it. So, in short, we can always gain access again if a boot image can be put directly into the SD card. And then we turn around to check the file system implementation of the gateway. After some, Googling, GitHub, and searching everything we can find, we found the Tesla may be using FATFS revision 9, which is written by CHAN, and they basically didn't change much config. And in the source code of the FATFS, we found before, there is a function in the code called FATFS rename, which is used to rename one file to another file. And in this function, we found it will strip leading spaces and dots of the new name. So if you rename A image to this is the space and B image, it would have the same effect with FATFS rename from A image to B image. And everyone can see that those two file names are different. And the string compare will return, or I don't know, positive or negative. Anyway, it's not 0. So here is a pretty simple exploit. First, we upload our customized update software to the gateway. We call it bad update image, sorry. And they rename it from bad update image to space, here leading space, and boot image. And here, the FATFS implementation of the gateway will rename it to boot image. So now you have a boot image on your SD card. And then reboot. And after reboot, your boot image is get executed. So this tells us never boot image without signature verify or without secure boot. You should always have a secure boot in your own hardware. And here is how we bypass the code signing protection. Let me check it. Yeah. Actually, gateway is a key part of the whole OTA process. And it's important to tell the OTA process to you. So next, I will cover something in the whole OTA procedure. First, let's check out some key critical components during the whole OTA process. The server, of course, it's OTA, so you have a server instead of a shop. And then the server will deploy a bundle to CID, which is a large screen you have seen. And the CID will deploy your firmware bundle to other components such as the gateway and SA, and most importantly, since ECUs, all those ECUs such as the ESP is not connected directly to the CID. So gateway will flash them using some customized protocols or something like UDS. Let's talk about the first part, which is how the firmware bundle is deployed. What is a firmware bundle? The bundle is a large file contains anything required to do a fresh upgrade on a Model S or Model S car. It's actually a SquashFS file, and this file is encrypted and is distributed through the CDN. So before we talk about those CDN things, let's talk about another module which is very important during an OTA procedure. We call it message box. Each car has a message box, and each message box contains lots of messages, and each message contains a command. So if you want to update a car, the server should put a special message into this car's message box. And let's say maybe I have talked about it. It's a Qt car. The Qt car is a process running on CID of the customer's car, and this process will pick unread messages actively. So here is the first step, which we call it handshake. The process Qt car will get if there are any unread messages, and if there are new updates available, Cloud would return with an initiate firmware handshake. And Qt car, after it has received this message, will send command do handshake to CID updater. After CID updater have collected this command, it will collect hardware infos. For example, if this is a full WD car, or if this car has an Autopilot ECU, and also collect software signature. And this signature is actually a checksum of the current firmware running on CID. After all those informations are collected, they will be sent to the cloud, which is a handshake server with a handshake request. And the cloud server will check if those information are correct, and if this car should have an update, and if so, it will return a correct handshake result. After handshake is completed, it's time to feature firmwares. So here is the second step. After CID updater have got the handshake information, it will verify there is a field called package signature in the handshake result, and the CID updater will check if this signature is correct. And if so, CID will read what we call it a download guidelines. It's actually something contains a URL from a CDN and a key and the checksum for the new bundle. And CID updater will download the firmware bundle from the CDN. And once downloaded, it will check its checksum and decrypt it if possible. After decrypt, of course, if there anything error occurred, it will just break. So, what will happen if something break? There have something we call job management, and this is the key part for Tesla's OTA. When you handshake, you will get a job ID, and you need to bypass several checkpoints during the whole OTA procedure. And the checkpoint name and related info and the job ID will be posted directly to the remote server, actually the handshake server. So we believe in Tesla, engineers might set up this with a pretty complex telemetry infrastructure. So they can make very quick response to if any bugs in their new OTA package. After the bundle have been deployed to the CID, now it's time to separate them through the car. Let's talk about the first step, which we call Ethernet-connected ECUs. Those ECUs are connected to the CID with Ethernet, and they all have an update agent. For example, for IC, we have IC updater, and for CID, we have CID updater. And they are sharing nearly same framework, although considering they are running on different platforms, the code may be different. Some code will be different, but most of them are still the same. And after CID got the firmware, it will distribute it to other update agents. For example, if we want to update IC, we will consider CID updater as a local server and IC updater as a remote agent. And both local server and remote agent would run a service. We call it command service listener. This service could be used to get a remote agent, which means local server, the CID updater, can get remote agent, IC updater if possible, if necessary, sorry. And when we say get, it means the local server can get any log message from the remote agent. And the local server can send commands if authorized to the remote agent. Again, we need to take IC as an example to say how a common or Ethernet connected ECUs is updated. Of course, the first step is that the remote hardware, the IC, need to get the firmware. After CID have got and decrypted the firmware from the cloud, it will get the IC updater, and send a new update notice command to the IC updater. And then IC updater will go to the stage we call the staged. And at the same time, basically at the same time, CID updater will start an HTTP server, which is used to provide some firmware files to the IC updater. And after both of them prepared, IC updater will download the firmware using the HTTP server we have just mentioned. After the firmware is downloaded, the firmware will be verified using info which have been provided in the new update notify. And the IC updater will go into another settings. We call it staging. And then it comes to step 2. You can see it basically works like Android AP update. There is A part is the running part, and B part is the backup part. The current software is running on A part. And the IC updater will just write the new root FS, the new DTB, the new kernel to the B part. And IC updater will try to switch 2 boot trains, the primary boot train and the recovery boot train, to part B. And then IC updater will verify if it had made changes to those boot trains correctly and verify if possible. And then the new firmware is now staged, and the new firmware on the B part is inactive now. Here is the general procedure. So you have got a new update, and the IC is go staged. And after the update is verified, the IC will staging. And after the firmware is ready to the B part, the IC is staged, and the new software is inactive. Finally, the IC will reboot itself. Now, the new software is active now. After we have talked about how the IC and other Ethernet connected ECUs are updated, let's talk about how gateway and other CIDs are updated. We call those ECUs connected to the gateway traditional ECUs. For example, the central body controller or front body controller or something like that. They will be connected to the gateway. And we have mentioned it, last year we have mentioned it, and previously we have also said that there is an updater called boot image, and there is a zipped file called release TGZ, and the updater mode file called UPD. And now we will introduce how all those files are picked and created. All of those firmware exists in a subfolder under the deploy folder. We have just said the firmware bundle is a squash FS, right? So there is a deploy folder and there is seed artifacts version 2. And in this folder, there are some important files. Updater, of course, you have to maintain this, the boot image, and a text file which describes the firmware version. We call it release version. And 2 TSV files. We don't know what is TSV, and we also don't know what is represents, but Tesla just use them. Those 2 TSV files are used to describe the firmware info we will talk about later. And another file is a TSV file, we call it internal options default. It will have some default configuration. And the last and the most important are many folders. They are named by the ECU name, for example, ESP, GCW, DAS, DAS, or something like that. And the firmware is stored in this form. For the ECU name, for example, gateway here, and the provider ID here. Provider ID here is 1, and the firmware name, I just read gateway fw.hex, but the actual thing might be different. And it's time to describe the TSV file. The TSV file would follow this pattern. The first line is always a version hash. And each line is following the same pattern. The ECU name, here GCW, and the provider 6. And the path to the firmware, like we have just said, GW1 models GWR4. And the new name, which means if you want to put this file into the release TGZ, you should rename it to gateway.hex. And the company name, of course, the GCW. And checksum, CRC32, of course. And some requirements. Requirements means if this firmware could be used under a 4W car or have a ESP interface or something like that. The last field is signature. This field, and also we have said the signed metadata map TSV are added after our bug report in 2016, and they are used to verify if the ECU firmware along with those informations are correct. So, after all those words, finally, how the file is created and sent to the gateway. finally. CID updater will pick up firmwares from the firmware bundle. And the CID updater will first get the car configuration, either for W car, either expensive or inexpensive, and some other configurations if possible. If the configuration it wants to collect does not exist in the current car, it will use what we have set the internal default options. And then those configurations will be compared with values in the send metadata to TSV. And it will pick the most suitable firmware as good as possible, of course. And pack the related file, GitHub hex or ESP hex, into related TGC. And after the related firmware is packed, it will also take the related line in the metadata TSV out into another TSV file exists in the related TGC. And the next step is create correct update file. For example, in factory, maybe we think in factory they will use factory UPD, and in service mode they will use service UPD file. And after those two files, along with the boot image are ready, they will be sent to the gateway. The boot image will be sent under the name no boot image. And the last step, of course, is the final step for the whole OTA procedure is send a command reboot for update with the argument boot image. No boot image, sorry. With the argument no boot image. So here is the whole OTA procedure. And after gateway restarted, basically, OTA server will deploy bundles to CID, and CID will deploy something to IC update itself. And CID will also deploy an update package to the gateway. Gateway will update all those ECUs, which is performed by boot image. And it will also update itself, the gateway itself, also performed by boot image. So, I wonder how many people have met us last year. Last year, we have also shown an Easter egg video. And the OTA procedure is what we use to deploy our firmwares into the different ECUs. And now Wen Kaizhang will tell us why, how we modified and patched those firmwares and how the whole Easter egg is working.
Okay. So before start my section, I want to ask how many guys here have Tesla already? And how many guys, personally, I want to ask a question. How many guys have BMW? Oh, no. And now I get this point, and so many guys without Tesla, and see some guys only have one Tesla to talk how to hack in Tesla. Oh, that's interesting. Okay, because I talking Easter egg, I want to ask, I want to illustrate one question. What is the Easter egg? You get some choice. The first choice is you can buy a Model X, and you can play the Easter egg from time to time, and you can play it. And I do believe the Tesla dealer will never tell you how exactly the Easter egg works. But now I can tell you how the more details about the Easter egg. And another question is why we last year to choose the release the video about the customer Easter egg. Because last year we released a video about how we control the vehicle, and last year why we choose to release the video, and this year we don't release any video. And so because a customer Easter egg shows our very deep study on the vehicle's ECUs, especially on the body control ECUs. And because we patched a lot of firmware in the body control ECUs to make our own Easter egg. And the Easter egg can be divided into 3 parts. The first part is about in the CID. It's about because if you want to trick the Easter egg, you should have a long press on the CID of the logo of Tesla. And then also the CID were responsible for the music playing. And another part is about the status check. Because you cannot trigger the Easter egg when the vehicle is on the highway, and when the vehicle is running, you cannot trigger the Easter egg. So to make safety, to make safe, and the Tesla will do some status check on different kind of canvas. And another important part is about the action and the lights part, because in this part, all the ECUs on the body control cam and all the ECUs relative to the body control will be attended to the Easter egg. And one of the most important ECU is about its name is BCM. Body control center. It can process some signal from the fob, and also it will trigger the final Easter egg. And now I think I can divide the Easter egg into 3 stages. The first stage is about the trigger on CID, because as an official Easter egg, you should first of all get in the car and have a long press on the Tesla logo and enter some passcode and to trigger the Easter egg, and then you should get you should be outside the vehicle and click the fob and trigger the Easter egg. Then all the Easter egg will start. So there are 3 stages. The first stage, it triggers on CID, and the stage 2 is the trigger and of the BCM, and then the Easter egg will start. So the first stage is about the triggers on CID, because after you have a long press of the T logo on CID, there's a signal from CID to send to gateway, and the gateway will transfer the signal to the body cam. And it will use the UDP Ethernet, because if you want to know the details, and you can check the white paper we released last year. And the stage 2 is about the fob signal processed, because when you click the fob, the signal will send to the BCM, and the BCM will send a signal on the body cam, and the body cam will transfer the signal to the CID to tell all the ECUs, let's get ready to start the Easter egg. And when we check the detail of the BCM, we noticed that the Model X fob has 2 kinds of signal. The first kind of signal is a very traditional signal. It's the 433 MHz, and another signal is about the BLE. And the BLE, because if you have a Model X, you will find out that the Model X will get the location of the fob, and it will open the door automatically for you. So Tesla used the BLE to get the location of the fob. And when the BCM node gets the signal from the fob, and it will send it to the body cam. On the stage 3 is Easter egg start, because all the ECU should be synchronized by 1 signal on the body cam, and we find out that the BC front will send the signal to tell other ECUs what action should be done at this, or should be do this moment. And then we find out something in the BC front. There's a very large scale of data. We call it Easter egg table. And the table, there's something defined in the table to define the actions, define the time, and the BC front will transfer the table on the body cam to tell other ECUs what to do. And so at a glance of the list, the table, you can notice that almost there are almost 10 ECUs in the Tesla attended into the Easter egg show. So it's really a big challenge and a very large reverse work, because you should locate the code in so many ECUs firmware. And that's why we choose to release custom Easter egg show. And now talking about how we do patch, because first is we should do patch in the CID, and then we should reverse the ECUs, and then I will talk about how we patch the ECUs. And in the CID, Tesla guys use a Qt core, and in Qt core, it will do some check. The first check is about the time. It will make sure the time is after Christmas Day, and also it will check the passcode. You should input the right code, and in the Qt core, it will check it. You should bypass these two checks, and also you should do another thing to use some hook technique skills to emulate, to simulate the user press in the Qt core. So that's a very large reverse work. And also when we talk about the reverse of ECUs, because it's very lucky, it's a good luck because all the body control ECUs are PowerPC. So you know ADA has a decompiler of the PowerPC, so you can it can make the reverse work be a little bit fast. And then we find out a string in the firmware. It's FreeSKU MQX. That's FreeSKU made RTOS, and this RTOS you can download some source code online. And one feature of this RTOS is about the segment table. At the very beginning of the initialization, the RTOS will, according to the segment table, to copy some data to the target address. And you can see that this table and at the beginning of the table, the source address and the target address are same, so it don't need to copy. But at the last three tables, you can find out the RTOS will copy some data from the room to the RAM. And that table will be very helpful to locate the Easter egg. Then we should, let me talk about something about the patch of BCM. In the BCM, when you use some reverse work, and you will find out one point will check the status of the fob. So you just need to patch this function and to bypass the the fob check. And let's go back to talk about the BC front. We find out it's very hard to locate the code of Easter egg, so we use some method. We compared quite a lot of versions of firmware of ECU firmware. Then at the exact version, we find out that one of the firmware suddenly become very large. And now you notice that the Easter egg must in it. And because Easter egg is very complex, there must be some data to illustrate, to indicate the motions of the all ECUs. So we quickly find the one firmware, and we find out the one segment in the data of the data become very large according to the segment table. So now we can buy some guess, and we can locate the egg table. And then when you in the ADA you check the reference of the egg table, you will find out there's a number which indicated the length of the egg table. Now at this moment you can get your own custom Easter egg. And now is my colleague doing to tell you how to route APE.
Thank you. Thanks, Wenkai. So on Tesla Model X, the Autopilot ECU is the most significant component which provides the driver assistant function. Like CID, there are few interfaces on APE for interacting with outside world. So on Tesla, APE, CID, IC, and gateway are on the same network. So firstly, we focus on the ports opened by APE. From the result of a map, there are four opened ports. Two of these ports opened by the binary APE updater. The first port supports an interactive shell and supports many commands. Some of these commands can be used by CID to upgrade the system of APE. The second port is the second part supports a simple HTTP server. In some situation, this server can be used to provide some file to other component. The command handshake will request a JSON from Tesla server. This JSON contains an URL to new firmware and other informations. The command install will pass this JSON and download the firmware. The command, the function M3 factory deploy is a new added command around version 17.17.4. This command and install command are unprivileged command and can be executed by CID without restriction. So the argument of this command is a JSON string. In this JSON string, there is a valid key, self_server, and the value is passed to a file. So when install command pass this JSON string, we can serve arbitrary file to the HTTP server. So in our exploit, we served Tesla 1 on HTTP server, and the log of APE updater shows Tesla 1 successfully served on HTTP server. We downloaded Tesla 1 from APE to CID and use its content to pass auth command. Now we can run system command with root privilege, so we enabled root SSH login and got a root shell on APE. Tesla fixed this vulnerability by forbidding function M3 factory deploy run on APE and adding a check of forbidden directories in function do serve. This vulnerability fixed in middle 2017, and the vulnerability exists only for less than 1 month. In conclusion, let me sum up our presentation. We talk about the vulnerability in WebKit and nvmap. We utilize them to gain root privilege on CID. We talk about how we bypass the code signing protection. Furthermore, we reviewed the details of OTA process. We explain how we customize Easter egg. Finally, we introduced the vulnerability we used to root APE remotely. Now we can nearly compromise all the components on Tesla, including CID, gateway, ECU, APE, and other ECUs. So we reported the vulnerability in CID and gateway to Tesla. Tesla fixed them very quickly and helped assign the 2 CVE numbers to the vulnerability in gateway and nvmap kernel module. So this is the second time we successfully hacked into the system of Tesla. But the whole system of Tesla is more secure than before. Apart from WebKit and kernel, the IP tables in CID and APE are more strict. In CID updater and APE updater, lots of bugs are fixed in history. Also, SXS token no longer used as a password, so the content of Tesla 1 cannot be used to pass auth command. The biggest security enhancement is the whole system does not support downgrade anymore. So I must say Tesla is really concerned about the security of their cards. So thank you. That's our presentation.